Hello, and welcome to this lesson on inverse trigonometric functions and integration. First, let's consider the derivative rules for inverse trigonometric functions. Derivative rules for inverse trigonometric functions are as follows. So, for the following derivative rules, u is equal to some function of x, and du is the derivative of u with respect to x. So u is f of x, and du is f prime of x. So here are 6 derivative rules for our inverse trigonometric functions. So the derivative of arc sine of u is equal to 1 over the square root of 1 minus u squared du. And the derivative of arc cosine of u is equal to negative 1 over the square root of 1 minus u squared du. Notice the only difference between these two is one has a negative and the other one does not. So what that basically means is if we take a look at the slopes of these two functions, then the slopes, their signs are opposite. Okay, so arctangent. The derivative of arctangent is 1 over 1 plus u squared du, and the derivative of arccotangent is negative 1 over 1 plus u squared du. So the same relationship we had with arcsine and arccosine, their derivatives, is the same relationship we have for the derivative of arctangent and arccotangent. So one of them has a negative, the other one does not. The derivative of arcsecant of u is equal to 1 over the absolute value of u times the square root of u squared minus 1 du. And the derivative of arccosecant of u is negative 1 over the absolute value of u times the square root of u squared minus 1 du. And again, the same relationship between arccosine and arcsine, their derivatives, and the derivatives of arctangent and arccotangent is the same relationship between the derivative of arcsecant and arccosecant. One has a negative, the other one does not. So, when we go to rewrite these rules for indefinite integrals, notice the following. So if you remember, the derivative of arc cosine was negative 1 over the square root of 1 minus x squared. So if I do the antiderivative of negative 1 over the square root of 1 minus x squared, that gives me the arc cosine of x plus some constant. But also, if we looked at it like this, well, if we put the negative in front of the antiderivative symbol, then we get the negative of the antiderivative of 1 over the square root of 1 minus x squared dx, which gives us negative the arc sine of x plus some constant. So, because of this relationship, because of the relationship between these two, anything that you can work with an arc cosecant, you could also do with an arc sine. Just the sign's going to be opposite, and you'll have a different constant. So because of the relationship between arc cosine and arc sine, their derivatives, and because of the relationship between the derivatives of arctangent and arccotangent, as well as arcsecant and arccosecant, we really only need three indefinite integral rules. We need 3 antiderivative rules. So here's our first antiderivative rule. The antiderivative of 1 over the square root of a squared minus u squared du. This is equal to the arc sine of u over a plus c. So here's our first antiderivative rule. Our next antiderivative rule, we've got 1 over a squared plus u squared du. That's equal to 1 over a times the arctangent of u over a plus some constant. And then our third one here, the indefinite integral of 1 over u times the square root of u squared minus a squared du is equal to 1 over a times the arcsecant of the absolute value of u over a plus a constant. So trying to take a look at these 3 rules, when I take a look at the first one and the third one, one way to notice a difference between those two is the following. this top one here, the one that gives me arcsine, this is a squared, which is a number. So I've got some number squared minus my variable stuff. U represents my variable stuff. So if I have number minus variable squared in the parentheses, then that's going to be an arcsine. Here I have variable squared minus number. So if I've got variable squared minus number inside of a square root, then that's going to indicate an arcsecant. Well, we also got a u on the outside, but looking at the inside of the square root, that to me is the big indicator, because the direction of the subtraction is important. A squared minus u squared is different from u squared minus a squared. Now the middle one, the one that gives me arctangent, I've got no square roots anymore. I've got a squared plus u squared. And since this is a plus, it really doesn't matter which order they're written. All right, well, I've got several examples prepared. And the way I've organized these examples, the first several examples are going to be examples that will integrate using arcsine. Then the next batch will be arctangent. And then the next batch will be arcsecant. So you can see some of the different ways some of these problems can be written. So let's take a look at our first example. Find the indefinite integral of 1 over the square root of 16 minus x squared dx. So my solution here, u is equal to x, a is equal to 4. That gives us u squared is x squared, a squared is 16. So when I do my antiderivative, this gives me the arcsine of x over 2 plus a constant. So that's my answer, the arcsine of x over 2 plus a constant. Let's take a look at another example. So example number 2, find the indefinite integral. So I've got the integral of 1 over the square root of 5 minus x squared dx. So my solution here, u is equal to x, a squared is equal to 5, which gives me a is equal to the square root of 5. So if I apply that same rule, that gives me the arcsine of x over the square root of 5 plus a constant. And then I chose to write my answer as arcsine of x over the square root of 5 plus a constant. Now I suppose I could have multiplied top and bottom by the square root of 5 and rationalized it, and you might see that written that way in some textbooks. Alright, so let's take a look at example 3. Let's find the indefinite integral for the following. So I've got the integral of 1 over the square root of 9 minus 4x squared dx. So here my u squared is 4x squared, which gives me u is equal to 2x, and my du is a 2 times dx. Now with the two previous ones, I didn't bother calculating a du because if u is exactly equal to x, then du is exactly dx. But since u is equal to 2 times x, I need to know what du is, which is 2 times x. And then if I solve this for dx, that gives me dx is equal to du over 3. And then my a is going to be a 3. So here I'm going to use my u substitution. So this integral is going to become 1 over the square root of 9 minus u squared times a du over 2. And then if I integrate this, this is going to give me a 1/2 times the arcsine of u over 3 plus a constant. And then going back, u is equal to 2 times x. So that ends up giving me a 1/2 times the arcsine of 2x over 3 plus a constant. Now I chose to write my answer as a 1/2 times the arcsine of 2x over 3. Sometimes it might be written as a 2/3 times x inside the arcsine. So there's a lot of different ways to write an equivalent answer. Let's take a look at example number 4. Now the difference between this one and the 3 previous is the following. On the top here, I have 2 terms. So since that numerator has two terms, I'm going to rewrite this as two separate integrals. So this is going to be the integral of x over the square root of 25 minus x squared dx, and then minus the integral of 3 over the square root of 25 minus x squared dx. And now I'm going to evaluate each one of these integrals separately. So for this first one, I'm going to use u substitution. I'm going to let u equal to the stuff inside my square root. So u is equal to 25 minus x squared, which gives me du is equal to negative 2x times dx. Solving that for dx, that gives me dx is equal to du over a negative 2x. And now I'm going to substitute that stuff in. So this gives me x over the square root of u times, and then dx becomes a du over a negative 2 times dx. Well, the x's are going to cancel, so I'm going to end up with a negative 1 over 2. And then that square root, that becomes a u to the 1/2 in the bottom of my fraction. And I'll do the integral on the second one second. Right now I'm just working on the first one. So this 1 over u to the 1/2, that'll become a u to the negative 1/2. And now when I integrate this, I'm going to add 1 to the exponent and divide by the new exponent. So negative 1/2 plus 1, that gives me a positive 1/2. And then dividing by a positive 1/2, that's the same thing as flipping the 1/2 and multiplying it. So that becomes a times 2 over 1. So the negative 1/2 times the positive 2 over 1 gives me a negative u to the 1/2 exponent. All right, well, I now need to take that u and convert it back to x's. So u is equal to 25 minus x squared. So this becomes a negative 25 minus x squared to the 1/2 exponent. And this is minus the second integral. So I did all that work just to integrate the first integral. Now let's integrate the second one. The second one is a pretty much straightforward arc sine one. So I'm going to have a 3 out in front, and I'm going to have the arc sine of x over 5 plus a constant. So my answer here is the negative of, in parentheses, 25 minus x squared raised to the 1/2 exponent, and then minus 3 times the arc sine of x over 5. All right, so let's find the following integral. The integral of 7 over negative x squared minus 10x dx. Now, in order to do this one, we're going to have to complete the square inside the square root. All right, so completing the square inside the square root, first thing I want to do is factor out that negative. So I get a negative x squared plus 10x. I take the number in front of the x, which is a 10. I divide by 2 and raise it by an exponent of 2. So 10 divided by 2 is 5, and 5 squared is 25. So after that calculation, that 25 inside this bracket, I have to add the 25 and then subtract the 25. So I get x squared plus 10x plus 25 minus a 25. Now, my whole reason for doing this is so that I could rewrite this. These three terms here can be factored, and they can be factored into an x plus 5 times an x plus 5, or x plus 5 squared. And then I still have this minus 25 here. Distributing my negative sign through, this gives me a minus x plus 5 squared, and a minus times a minus gives me a positive 25. So by completing the square, I ended up taking something that did not look like we could integrate it, and I've turned it into something that fits that arc sine format. So my u is x plus 5, and my a is going to be a 5. So the coefficient out in front is 7. So when I integrate, I get 7 times arcsine of x plus 5 over 5 plus a constant. So there's my answer. 7 times the arcsine of x plus 5 over 5 plus a constant. All right, let's take a look at some that utilize the arctangent one. So find the indefinite integral for the following. 5 over 7 plus 4x squared. So u squared is going to equal 4x squared. So that gives me u is equal to 2x. And du is going to be 2 times dx. Well, that gives me dx is du over 2. A squared is equal to 7, so that gives me a is equal to the square root of 7. Using u substitution, this is going to end up giving me the following. So that gives me a 7 plus u squared, and then times the dx becomes a du over 2. So my 5 over 2, I put that out in front, so I have 5 halves times the integral of 1 over 7 plus u squared, which when I integrate this will give me a 5 over 2 times 1 over square root of 7 times the arctangent of u over the square root of 7. Now my u, that was 2x, so this gives me 5 over 2 square root of 7 times the arctangent of 2x over the square root of 7 plus a constant. So my answer is 5 over 2 square root of 7 times the arctangent of 2x over the square root of 7 plus a constant. Or if you decided to rationalize these, multiplying top and bottom by square root of 7s, this one I decided to rationalize it just so you can see how it could have been written. This gives me 5 times the square root of 7 over 14 times the arctangent of 2x times the square root of 7 over 7 plus a constant. Now let's take a look at number 7. So this one, we're going to have to do a completing the square. So this one, I'm going to factor a 2 out of that denominator. So that gives me 2 times x squared plus 6x plus 25. Now one of the nice things about this one compared to two problems earlier, is this 2 is not inside of a square root, so I can just bring that 2 outside, and I can write this as a 3 over 2 times the integral of 1 over x squared plus 6x plus 25. So now let's continue my completing the square. So take the number in front of the x, which is a 6, divide that by 2, and then square it. 6 divided by 2 is 3, and 3 times 3 is a 9. So I'm going to add 9 and then subtract 9 in the bottom of that fraction. So I've got x squared plus 6x plus 9, and then a minus 9, and then here's my plus 25. The whole reason for doing this is to get these three terms, x squared plus 6x plus 9. This x squared plus 6x plus 9, that will factor into an x plus 3 times an x plus 3, or x plus 3 squared. And in the rest of this, the negative 9 plus 25, that gives me a plus 16. Alright, so what we have done is we've taken something that we could not integrate and we've now rewritten it into a format where our arctangent will work. So I've got 3 halves times a 1 over 4, that's the square root of the 16, times the arctangent of x plus 3 over 4 plus a constant. And then my 3 halves times my 1/4, that gives me 3/8 times arctangent of x plus 3 over 4 plus a constant. All right, here's another one. Let's take a look at this. So I want to find the indefinite integral of this. So I've got the integral of e to the x over e to the 2x plus 1 dx. So, using some u substitution, u squared is equal to e to the 2x, which means u is equal to e to the x, and my du is equal to e to the x dx. Solving this for dx, this gives me dx is equal to du over e to the x. So start rewriting this thing. So this gives me a u squared plus 1, still have that e to the x on the top, and then the dx, that becomes a du over e to the x. And then the e to the x's cancel, and I end up getting the following. The integral of 1 over u squared plus 1. So this problem up here did not, at least to me, it didn't look like it was going to be an arctangent at the beginning, but after manipulating this, doing a u substitution, it now looks like an arctangent will fit with it. So when I integrate this, this gives me the arctangent of u plus a constant, or the arctangent of e to the x plus a constant. Let's take a look at another one. Let's try this one. Find the indefinite integral. So I've got 1 over e to the x plus e to the negative x dx. So, rewriting this one, I'm going to multiply top and bottom by e to the x. So 1 times e to the x is e to the x on the top. When I multiply the bottom by e to the x, remember when I distribute through, since the base numbers are the same, we have to add our exponents. So e to the x times e to the x plus x is a 2x. E to the x times an e to the negative x plus a negative x is 0, and anything to the 0 power is a 1. So after doing that manipulation, this example now looks like the same problem from example 8. That's now the same problem from example 8, and the answer to that was the arctangent of e to the x. So the answer to this one is also the arctangent of e to the x plus some constant. So one of the things I want to kind of point out is, even though I'm trying to do lots of different examples here, there's no way I can actually do an example of every single possible thing that you can see. What this becomes is trying to take something and work with it and put it into a format that we can work with. And in this lesson, the 3 formats we're trying to build are these 3 formats. So in this lesson, we're trying to make our problems match these 3 formats so we can integrate them. All right, let's take a look at our next example. All right, so let's find the indefinite integral. So I have the indefinite integral of 5 over x times the square root of 4x squared minus 9 dx. So using my u substitution, u squared is equal to 4x squared, u is equal to 2x, du is equal to 2 times dx. Rewriting this, this gives me dx is equal to du over 2. So starting to do my substitution here, well, that 5 that's in the numerator, I'm going to bring that out in front. My dx becomes a du over 2, and my 4x squared becomes my u squared. Now notice we still have an x in the problem. We've got to get everything turned into u's. So we're going to go back to this part right here. U is equal to 2x, and we're going to rewrite that and solve it for x. So that means x is equal to u over 2. So plugging that in, well, I got this 5 out in front, times the integral of 1 over u over 2 times the square root of u squared minus 9, and then a du over 2. This 2 and that u over 2 When those multiply, the 2's are going to cancel, and I now have this. 5 times the antiderivative of 1 over u times the square root of u squared minus 9 du. So again, what I've done is I've made this problem fit that arcsecant format. So integrating this gives me 5 over 3 times the arcsecant of the absolute value of u over 3 plus a constant. All right, u was 2x, so this gives me 5/3 times the arcsecant of the absolute value of 2x over 3 plus a constant. 2 is positive and 3 is positive, so I'm going to write that as 5/3 times the arcsecant of 2/3 times the absolute value of x plus a constant. And there's my answer. All right, let's try another one. All right, so we want to find the indefinite integral. So the integral of 1 over the square root of e to the 2x minus 4. So using u substitution, this gives the following. U squared is equal to e to the 2x, u is equal to e to the x, and du is e to the x dx. So, solving this for dx, that means dx is equal to e to the u, or excuse me, e to the dx is equal to du over e to the x. So substituting this stuff in, my e to the 2x, that becomes a u squared. My dx becomes a du over e to the x. Now this time, when we did our substitution, we introduced some x's. We still have some x's in here. But remember, e to the x is the same thing as u. So this e to the x is a u. And then rewriting this gives us the integral of 1 over u times the square root of x squared minus 4 du. And now this fits my arcsecant template. So integrating, whoops, there should be a coefficient of 1/2 out in front of this. I hate mistakes. So this should be 1/2 in front of this. Please remember 1/2 in front times arcsecant of the absolute value of u over 2 plus c, which should give me a 1/2 out in front of all this. Arcsecant of e to the x over 2. 2 is positive, and e to the x is always a positive function, plus c. So my answer is going to be 1/2, don't forget the 1/2 out in front of all this, the arcsecant of e to the x over 2 plus a constant. All right, one last example. So let's say we want to find the indefinite integral for the following. So I've got the integral of 6 over x times the square root of x minus 9. Now again, when I look at this, it doesn't seem like it should fit any of those formulas, but let's give this a shot. So I'm going to let x squared equal to x. I'm not x squared, u squared equal to x. So if u squared is equal to x, u is the square root of x, which is the same thing as x to the 1/2. When I take the derivative of u, du gives me a 1/2 x to the negative 1/2 dx, which is also the same thing as saying dx over 2 times x to the 1/2. Solving this equation for dx, that gives me dx is equal to, well, multiplying by the bottom, that's 2 times x to the 1/2 times a du. So, well, now let's try to do my substitution. The 6 on the top, I'm going to bring that out in front. And I've got 1 over x times the square root of u squared minus 9. And then my dx becomes 2x to the 1/2 du. Well, my 2 is just going to be a 2. Since I have an x to the 1/2 and an x on bottom, so those are going to reduce, and that leaves me with a single x to the 1/2 on the bottom. And then if you remember from here, x to the 1/2 is what u happens to be. So 2 times 6 is 12, and I get 1 over u times the square root of u squared minus 9 du. So again, what I have done is I've taken something that does not look like it fits that arcsecant formula, and I've rewritten it so that it matches the arcsecant formula. So integrating, this gives 12 over 3, arcsecant of the absolute value of u over 3, plus a constant. U is equal to the square root of x. The square root function is always positive, 3 is always positive, and 12 over 3 gives me a 4. So my answer is 4 times the arcsecant of the square root of x over 3 plus a constant. Thank you for watching this lesson, and I hope to see you next time.